and Dr. Neeraj for inviting me to this talk. Now, I'm going to talk about a different topic, which is probably not controversial, although there are a lot of innovation that needs to happen in this area. I call Scaffold as the story behind every successful repair. I work at Reliance Hospital in Mumbai, and I'll start with this Mona Lisa picture. And this slide on the left side of the screen is the Mona Lisa picture of orthobiologics. Whichever angle you look from, you'll find the cells, growth factors, and scaffold playing a role in regeneration. And I use this analogy a lot of time when I teach my students, DNB as well as primary MBBS students. Imagine going from Mumbai to Pune. You'll need three things. You'll need people in the car, you'll need highways, and you'll need fuel. And this is the representation of entire orthobiologics story today. So you need cells, which are primarily car. You need good fuel, which are the growth factors. And you'll need a good infrastructure, which is Mumbai-Pune Expressway. So if you've got all these three sorted out, you will reach safe and you will reach your destination. And that's the story with the entire orthobiologics today. When we look at the cartilage repair and we look at what are the options, we need few things. We need basilar integration with bone and calcified cartilage. We need them to have integration on the sides, which is the marginal integration. We need the defect to be filled, and ultimately we need the cartilage to be stratified in something of this form. So we need healing from down, we need healing from the side, we need the adequate gap to be filled, and we ultimately need some kind of structure to form when we look at the cartilage. And that is what the scaffold do. They act as template to promote cellular interactions, promote extracellular matrix formation, and of course the structural framework for regenerate. We've got a lot of options when we don't use scaffolds, but there's always a morbidity of donor side. We require second procedures when we consider ACI. Allografts has the issue of donor availability, and there is limited shelf life. So scaffolds are temporary structures. When we look at these, they by definition are temporary structures. But in our case, it's a physiological powerhouse. And how we judge each scaffold, there are certain standards that we need for scaffolds. There are certain properties, and we need them to have certain abilities. And this is going to get boring from here because a lot of it is biochemistry and biomechanics. So we look at standards. So of course, the scaffold should be biocompatible. Without that, we can't implant. They have to be biodegradable. They have to be non-immunogenic and non-toxic. So these are the most important features that we need to have in scaffold. But as surgeon, Dil Mange More. We need more things from the basic things. So we want it to be cheap. We want it to be available. We want it to be easy to use. We want that there are less post-op restrictions, and we need an expedited recovery. So these are some kind of things that this is the wish list that we have. And as I progress, we'll talk about each scaffold option that we have. Now comes the basic scientist. Now they talk about scaffold in terms of porosity, they talk in terms of interconnectivity, surface property, mechanical strength. Basic words to just remember, and each of these properties have certain role. And then comes the ability. It doesn't stop. So it gets more and more complex. So we want cellulation, we need growth, we need reorganization, neovascularization. So if you look, there is biology, there is biomechanics, there is wish list, and that is what constitutes a scaffold talk. When we classify, of course, we classify on the basis of whether they are synthetic, whether they are protein-based, carbohydrate-based combination, or they are biospheres where we have got these bioactive scaffolds. And natural product, most of the natural products have been collagen, hyaluronic acid, alliginates, chitosans, and gelatins. So these are the basic natural products that have been always used as biocompatible things. And over time, as we have seen with suture material, the synthetic things have come. So which are PGA, PLA, PEO, PLGA, PCL. So again, different kind of polymers have come in, just like the suture material that we use. For us, however, the classification is two broad classifications, whether they are cell-free or they are cellular. And there is a structural classification, which means that whether they are monophasic, biphasic, and multiphasic. That is why I said it's going to get boring, because there's a lot of things and technical aspect. But I'll just simplify in two characters, whether one is mechanical character, what we expect, and the other is the biological character. So when we look at physical character, we need that they should allow early weight bearing. So they should have sufficient strength to allow weight bearing when they have. Again, the structure has to be a three-dimensional structure so as to allow all the biological properties to enhance healing. So these are the two physical characters that we need to look at a scaffold. And biological character is biocompatibility, as I said. That the other thing is that they should be degradable, and then they should afford some kind of bioactivity. Now, this is a slide that I've taken from Insol, and the new Insol has this complex, busy slide, but it has got a lot of value because it kind of gives you an insight into how you can differentiate between different broad groups of scaffold. I'm not going to go into detail because it will become more and more boring, but you see all these words keep coming: biocompatibility, the strength, the ability to attract growth factors. So broadly looking, your highway should be and I come back to this highway example, your highway should allow cells to pass. They should have petrol pumps on the way. So if you have growth factors available on the way of the highway, it's excellent. It should be the highway should offer a non-bumpy ride. So two basic things, and it should be able to withstand over and over repeat usage. So three things if we have on a scaffold, I think that solves a lot of problems. And then we started with the first generation of scaffolds were matrix scaffolds. And you will see that there are a lot of commercial names available, but we all have heard about ACIs or MACIs. So the first scaffold were porcine collagen 1 to 3 types, and this was by a company called Vericel. They allowed a horizontal sheet of cells to form. And shortly afterward, the Anika Therapeutics came in with a hyaluron-based cells called as hyalugraft. We have had a lot of discussion about hyaluronic acid in the morning, and these were in kind of sync with this whole thing. So this is how it used to look like, the chondroclite. So you'll see that all the defects could be made, and there were sheets on which these things were grown. And then this is another generation of scaffold which is called as BST Car Gel. It's important because it's one of the Indian companies, the Piramals, but the Canadian research arm of Piramals developed this product, and it was later brought in by Smith & Nephew. So there's some indigenous research, and I thought that I'll at least mention. It had the crustacean shell divide chitosan mixed with blood in 1:3 ratio, and this resulted in formation of a polymerized hydrogel which could be implanted into our target site. So something of this sort. This is again from company manual. You inject the blood into this bottle and then aspirate it and inject it into this area. This is how the car gel works. Another one, this one was from Arkiva from Israel. So again, all of these are matrix modulated myostimulation technique and consisted of biodegradable photopolymerized hydrogel. So technical terms, but this is how it used to look like. So these are gel-like things, and that could be implanted. The other thing is again chondrotissues. So a lot of products are there when we look at the scaffold thing. So it's a PGA hyaluron implant. It is immersed with the autologous serum or platelet-rich plasma and implanted into the full thickness cartilage defect, and you do a microfracture before this. It can be fixed with a Fibrin Glue or bioresorbable implants such as smart nails. And I said over the time the thought process came into more structural things. So we have a multi-phasic scaffold, and most popular of this is Tru Fit, which is again by Smith & Nephew. So it mimics the physical and mechanical properties of cartilage and bone, composed of polygraphed a porous hydrophilic material composed of an 85 to 15 ratio, PLA and PGA and PLDG, along with calcium sulfate. So that is how the multiphasic or biphasic scaffold came in, and these are the plugs. So this is an example of a Tru Fit plug. Now, more and more companies came into this, and MyoRegen is one of the companies which is by Fin Ceramica. It might be available soon, so I put it in there. Then Chondromimetic and AGLC. So if you look at these things, now I'll just tell you, of these, none is available in the country so far. The first one that is going to be available soon is the MyoRegen, which is expected to come in January, and it has received an FDA approval, or the Indian FDA approval for this. So the Fin Ceramica one is the only one available of all the things that I mentioned. But as I said, that these scaffold can have additions with anti-angiogenic drug, parathyroid hormones, TGF, and cadherin, so they can be tailored to your use. As I said, your fuel could be implanted in the car to drive you to a certain destination. I'll quickly talk about our preferred technique, that what we use with what is available. Now, jugaad is a bad word. So scientific things, people will not like jugaad. And I really liked when Pradeep said that multiple anecdotal evidence does not constitute data. So I'm not going to bore you with data that I have, although we do collect the data. The first thing is do no harm. So we followed at least that basic tenets of the scientific thing. What we use is these three common products. I work at Reliance, so we've got good research facilities for Relic, which is like TCL is the other product. We've got this gel foam that we have been using for centuries, at least a century, I guess. And the safety is proven. And the third is the concentration mechanism. We did some background search on to find out the gelatins that were used in past for these things, and we found that the constitution is the same. And we also went in to find out whether they have got any adverse reaction in terms of usage. And a lot of data was from spine, and there's very minimal usage with this. So we use the combination of these three at the moment with what we have available. We create a microfractured lesion, put the fibrin glue, then put the gel foam over it, and then put finally the concentrate. So this is our technique of what we use. We call it a sandwich technique, derived from the GCT treatment to use. That we have got one layer microfracture. We do not violate. One thing that we do not do when we do microfracture is to violate an osteochondral plate. So I think that's detrimental. We just go in deep enough. We put the fibrin glue as the first layer. We put the gel foam, and the third layer is the cell. So it's a kind of a three-dimensional structure. Jugaad three-dimensional structure, but that is what we think, what we do. We fix it with glue, we provide a scaffold in form of a gel foam, and we give cells which is exogenous, and of course the microfracture would give some endogenous cell. That is our belief. We don't have long-term data, few patients at the moment because I work not at very high volume centers, but we are collecting data, and once they come in, we'll have it displayed shortly. I can't end this talk without talking about 3D printing, another area of my interest, and we use it a lot for our joints patient and 3D modeling. And I think this is another area where the 3D printing is going to have a lot of role, because as I said, all the scaffolds, all the highways have to have three-dimensional thing, should allow the cells to move in, cells to home in, they have to have a homeostasis. So there are two approaches. So top-down approach where the cell was seated into a biodegradable and biocompatible scaffold and fill the scaffold and create matrix. Whereas there is another new approach in 3D printing which has come up, which is called as bottom-up approach, and it consists of cell encapsulation with microscale hydrogens. Bioprinters look something like this, technical thing, but basically I call this the jalebi maker. You can have a layered thing, only thing is the extruder moves, instead of by moving a hand, it's got a computer program, so it can print different objects. So if you look at the plotting material, so you can have cells, you can have one phase of cartilage, so which can be more solid like calcium phosphate, the other one can be a gel. So if you have all the three components and they can be plotted on a bioplotter, I think that's the future of the entire regenerative medicine, be it cartilage, be it liver, be it the kidney. A lot of work is being done in Drexel University, and I think they are one of the pioneers, these bioplotters. And I hope that in future, most of the regenerative medicine would somehow focus into this. In cartilage, it has made a lot of strides. This is the alginate scaffold, which is soon going to be available, I'm told, which are 3D printed. So when I talk about scaffolds and cartilage, I said we can't outsmart God. So we have to work out, we have to outplan and outgive. The take-home message is again coming back to that first slide we had. So this is the three things. You need scaffold, you need cells, and you need bioactive molecules. And this is how all the things have controversies and the proven things, and in between is somewhere what we have, the true tissue engineering. Again, this is a very busy slide, but two distinguishing things: cell. The top one is the two-step one, and the bottom one is the single-stage scaffold repair. Again, a lot of experimentation and innovation going on. So in the end, there is take-home message that there are many products, but there are few level 1 evidences for each of these scaffolds. Innovation is the way forward. We have to understand the basic and customize the solution to each patient. We have to be aware of hype and marketing, because our foundation has to stand the test of time. It should not happen that our inspiration today is tomorrow's revision. Thank you.